This is the real number line. Now, normally we draw the real number line with arrows on each side. You can do that in Desmos by clicking the gear icon and clicking arrows, and that will show the arrows here. It doesn't really matter. It doesn't affect anything with Desmos either way, because Desmos extends it indefinitely. You can just click and drag, and as you can see, as we go to the right, the numbers get more and more positive. And then if I hit the home button here, it'll go back to the 0 point. And as I go to the left, the numbers get more and more negative right there on the number line. And of course, home brings us back. We can also adjust the view of the lines and everything by going to the gear icon and then changing this. We're not dealing with the y-axis right now. We're just dealing with the x-axis. So right now we're at from negative 10 to 10. I can, of course, go like from negative 100 to 100. And note that the scale on the axis changes. So it doesn't actually look like the number line changed, just the scale changed. In fact, if you scroll out with the wheel, you can see that the scale is getting larger and larger. And if you scroll in with the wheel, you're zooming in and the scale gets smaller. You can also do that with these plus and minus icons or buttons. And the nice thing about using these is that it really centers it on the point that you're looking at. Whereas when you do the scroll wheel, it kind of zooms in where the cursor's at. Of course, the home button gets you always back to 0, 0. So that's an important one to use. It's not there when you're already there, but you just deviate from that, the home button shows up, and that's what you have there. Okay, so now we're going to plot some points, and plotting points in Desmos is going to require a coordinate pair. Now, because we're working with the real number line right here, technically you wouldn't use a coordinate pair, but Desmos only interprets coordinate pairs for points. So that's what we're going to have to do here. Of course, normally how we would do this is we just write like x equal to 1, but you can see that Desmos interprets that as a vertical line. You can kind of flatten this into this point right here, and that would be effectively what it is, but this is the point that Desmos really wants you to point to plot, and 1, 0, that's going to be the point. I'm just going to get rid of this x here, but you can see that I typed the beginning parenthesis, which is just shift 9, and then I have not typed the last parenthesis there. Desmos automatically interprets it into there, and you can either get it in there by just clicking off of that, and it'll automatically add it, or you press enter, and that will automatically add that second parenthesis, and it'll complete it for you. And there you can go. You see we have the point 1, 0. We can adjust this point's settings. We can give it a label if we want. We'll do 0.1, for instance. That gives us a label. I'll turn that off for now. I can also just click and hold on this blue, and I can change the color of it to red or green, orange, whatever. And then I can also change the point's shape. And this is going to be I believe this is the opacity. So if you can see through it or not. If it's 1, you can't see through it. And then this is the size. So if I do like 100, you can see it's a big star there. So of course the label is there, and that just shifts where the label's at all around there. Most of this time you're not going to really need to use this stuff, but it does help to change the colors and the shapes, as well as sometimes the actual size. Okay, let me make that smaller here. Okay, so we can also plot more points by just doing again the coordinate pair. Because we're using 2 dimensions here and only on the x-axis, we're only going to put numbers in the first spot. The second spot is reserved for y, but we're not using y-axis right now. So of course if I do like a negative 14.324, you can see that's not on here, but all I have to do is just scroll over. Oops, I forgot the coordinate pair plot. There we go. And there it is, negative 14.324. And if I want to do a really large number, we'll do like, let's see, 1 billion. And then put a 0 in there. To get there, let's just zoom out a ton. And there we go. It's right there. Of course, I could have also just gone to the home screen and then adjusted the axis to see. Let's do 2. A little bit easier to see if I do 2 million right there. There's the point. This is 100,000, not 1 million. 100,000 0. So that's different ways of changing the view to make sure you can see what you're looking at. Let's go back to the home. Okay, as you can see, we've been plotting points using this expression bar on this side, this navigation kind of window thing. All of these things are expressions, and you can do more than just expressions in here. You can also do, this plus icon shows you, you can add expressions, notes, tables, folders, images. Tables are really helpful when you want to plot a bunch of different points. And we're of course only going to be using 0 for the second spot because that's going to be the y coordinate. If I just add 0 there, it's going to just add zeros for everything. And then for the first spot, I'm going to add things. Let me turn off these points. I can turn off these sides points by just clicking on them, and that'll turn them off from the view. And then this one shows this screen. That means that it'll plot it. If I just click that, it'll not plot it. Okay, so let's do 1, 2. Oops, let me not use the comma. I don't know why I put that in there. 3. If I hit enter, I go down. 4. It automatically put 4 in there. And 5, 6, 7, 8, 9, 10, 11, 12. And I can just hit enter and I can see all that stuff. And this, of course, is the natural numbers. 1, 2, 3, 4, 5, 6, 7, all the way on up. These are all the natural numbers. And then, of course, it would have to continue indefinitely for that to be the entire natural number set, which I can't do here, but you get the idea. I can plot a bunch of points very quickly using a table. Of course, if I add 0 to this, let me see if I can do that really quick here. Yep, I just hit enter on by clicking this and I added a spot there. If I add 0, 0, and then include all of the whole numbers on up to a positive infinity, these are the whole numbers with 0. And then, of course, if I add in the negative whole numbers, then that would be the integer set. And from there, it's going to be a little bit more tricky to talk about since the rational numbers there's like infinitely many of them between 0 and 1, so I can't really show that effectively here. But that's just the basics of sets using this, and then of course the points, plotting points with a table and the coordinate pairs. Let me actually show you a couple of negative numbers here just to make sure you can see that nothing's weird. And 4.2, negative 15.896, negative 100. So it is plotting these as well. There's nothing special about positive numbers. Negative numbers will plot as well. There was negative 4.2. We had negative 15.896. And then, of course, negative 100. I have to zoom out a little bit to see that this was all the numbers that I first plotted. But there's negative 100 right there on the number line. Okay, so I've shown a table of values there, and I've shown individual points, but in general, we like to use variables and sliders in Desmos to show like a lot of variety in one succinct expression. And so to do that, what I'm going to use is I'm just going to delete all that stuff. I'm going to use a variable a0, and you can see that Desmos adds a slider for a because it understands that you're using a variable there. If I click that, then you can see that it adds a slider from negative 10 to 10. I think it's in, 0.1s. That's the scale. And you can see here that it's sliding this point along the x-axis. That's because a0, right? This would be 1.10. Well, that's that point right there. If I move it over here, 5.50 is this point right here. You can see that it's also showing in that expression window what that equals. And of course, I can slide it down over here. Because this is a slider, I can actually, you can see that Desmos recognizes this as moving left and right. I can actually grab the point itself on the grid and move it around. It can only go left and right. I haven't given it any vertical movement, but I have given it that freedom there. I can change the bounds on this by just clicking on either one of the two sides, and I can change the bounds here. So I can go like negative 100 to 100 in steps of 3, for instance. And then you can see that it goes from negative 4, negative 7. It's going only in steps of 3. It won't go anything between that. And then, of course, if I go way up here, I have to zoom out a bit to get a 62. There it is right there. And if you click and drag, it again will not do anything besides these steps of 3. It's a little bit weird because the steps of 3 doesn't fit exactly on the bounds I gave, but Desmos still can interpret it just fine. So there's nothing special about the variable a. I use that one just because that's the first letter in the alphabet. B works just as well. So if I do B0, you can see that it says add slider there for B, and it'll be a different color, and I can just move it independently of this one. So they're two different points. And even though it has the bounds here, but I'm zoomed out, I can drag the point and I can go beyond the bounds, and it'll just change the bounds for me. That's one helpful thing that Desmos does. But if you only use the slider on this thing, it will only restrict it inside the bounds there, which is helpful in case you want to play the point, which you can just click that play, and it'll automatically go through the range. This is useful for animation if you wanted to do animation in Desmos. So variable names, A, B, C, D, those letters are great because they're the first letters of the alphabet. They're not they're typically used as constants in mathematics, but Desmos will understand them as variables. There are some things that are reserved, however, and you can't use. So something, for instance, like E. If I use E0, you can see that it doesn't give me the option to add slider. That's because E is a reserved mathematical constant. The E is Euler's number. It's 2.718. It's approximately 2.72. Also, X is a reserved variable. You can see that it just doesn't interpret it as anything, and it gives you a flag there, and it says it doesn't know what to do with what you've written. So X and Y are reserved variables. Z is also not really reserved, but it is used in a lot of different contexts. Same thing with T. Sometimes we don't like to use the X as the axis, but we like to use T as the axis. But I think we can still add a slider for T. It'll actually give you a range. It understands it as a range of values in time. It's kind of a more confusing one. I think S will work though. Yep, S. You can add a slider there for S. Now, instead of just using a variable like this, we can actually make a name out of the variable, and that will make it much more interpretable by Desmos as a variable itself. And you can do that really with using subscripts. For instance, I can't really do two letters right next to each other because it'll recognize that as two distinct variables that are multiplying. Instead, I have to use a subscript. So I use shift hyphen, which is the key right next to 0, just to the right of 0, and that adds a subscript there. And so I can add a name here by using something like this. I can do slider, and you can see that it adds a slider for slider. You can add more than one word. You can't use spaces. That doesn't make any sense for Desmos. You can see that it flags it there. But what you can do is use capital letters to distinguish the different words. So for demonstration, and there we go. It adds a slider for demonstration. Just be aware that sometimes this can be confusing, and what might make sense to you may not make sense to someone else if they're going to read it. But if you're just using it for you, then you can name it kind of whatever you want. But that's a way of getting around the limited variables. You just create a name out of the slider or the variable itself. I want to show this a little bit in more context with the sets of real numbers. And for that, I can either name them, or I can just use the variables a and b, since that's very easy to use and they're already available. So I'm going to delete all this stuff again and just restart. So I'm going to use a, 0, and I'm going to set the bounds to be 1, 2. I can do like something very large in steps of 1. And technically this is supposed to go to a million, to infinity, but it only goes up to a million. So it's not quite equal to the set of natural numbers, but you get the point. Like this just continues indefinitely, and only these numbers are going to be in the the set of natural numbers, the counting numbers that we use. That's the most basic set of real numbers that we work with. Of course, you can zoom out a ton and you can just drag this out. So all of these numbers are just, the whole numbers. There's no decimal part in the natural numbers. Now, if instead of this, I added onto this 0 in addition to, so it's 0 is less than or equal to a, it's less than or equal to, technically it's supposed to be infinity, but I can't go to infinity here. So just, think of that as infinity. This is the set of whole numbers. So it includes 0 and it includes every single positive whole number with no decimal part. That's the set of whole numbers in the set of real numbers. So again, let me add in an expression here. I'll do it like this. So I'm going to add in, I'm going to add in a note here. So this is going to be the natural numbers. That was a from 1 to infinity. And then here, I want to add in a note and say, you can see that the note's designated here with the quotes. This is going to be whole numbers. And that's going to be, I'll do B from 0 to infinity, but I can't do infinity in steps of 1. There's no decimal numbers in there. Okay, and then we can do a note, and then we can do the set of integers. The integers are really the most important set of these types of numbers. If we're talking about the natural numbers, we typically talk about the positive integers. The whole numbers would be the non-negative integers. Since integers is more encompassing, it's just a better set to use. That would be, I'll do C 0, and then that's going to be from negative infinity, so I can't do infinity, but just a really large number there, to positive infinity. I'm just going to add a bunch of zeros there in steps of 1. So it's not going to be any of the decimal numbers, only the whole numbers that are both positive and negative. As you can see, those, of course, the wholes can't go below 0, and the natural numbers can't go below 1. So that's the kind of basic sets. And then the last one I'm going to show here is just the rational numbers. Rational numbers are the, you type it out here, rational numbers. This is going to be the set of all numbers that form two things. So I'm going to add two sliders here. I'll do it like this, just because it's easiest. It's kind of hard to add a slider on its own, but you can just add in. Well, if I just type the variable, let's do in for the numerator. Yeah, it doesn't want to add the add slider button, so I'm just going to add it in a point. 0. You can see that it adds a slider there for me. And then I'm going to add in the denominator. And so I can get rid of these two. That was just to add in the sliders. And the rational numbers, I'll just move this down here. The rational numbers are all integers, are all fractions where the numerator and denominator are integers. So I can add in numerator divided by denominator. I'm using those subscripts again to designate the actual names, so it's clear to see what I'm talking about. And then I have the same color here, so I'm going to just change this color to, let's do red, since I've already got green, blue, and black used. And now, again, these can be anything super large and super small, but whole numbers, so it's up to 1. The same thing too here, because again, it was all integers in the numerator and denominator. And so again, think this is going to negative infinity to positive infinity for both of these two sliders. I'll flip this around since numerator should be on top. And that is the set of rational numbers. And of course, I can change this. It's going to be hard to show it on the graph because I've made it super large. And some of them are going to be like this. Like, for instance, that one, if I go back to the home screen, and I can find that one over here. Oh, sorry, it's negative 25.333 right there. And then of course I can actually drag it, and you can see that's only changing the numerator part. That's because if you're gonna have it should just change the top. If I do flips around, does it change that one? No, it still changes the numerator because that's the most easiest to understand when you're changing this line here. It can't change both. It wouldn't be able to understand which one to do for that. But you can of course just change this here. If I make them smaller, it's gonna be a little bit easier to work with. And so now, what you can see here is that I can get any kind of, go to the home screen. Let me turn off these two so it's just clear to see. These three. And I can get any kind of rational number here in the center. Of course, if it's the denominator is 0, this is undefined since you're dividing by 0. But any other rational number in there, it's all kind of showing right there. So that's a set of rational numbers. Okay, the last thing I want to show in this simplistic view of Desmos is intervals. So intervals are Desmos understands intervals in certain contexts as long as it's written a certain way. But it's going to be kind of weird in this one-dimensional view of things. So for instance, if I write x less than 1, you can see that Desmos will shade in. It's using 2 dimensions to understand this, but effectively we're just looking at this x-axis. We have 1 here, and x is less than 1. Well, that means it can't be 1, which is why there's a dotted line here, but it can be anything less than 1, which is why this side is shaded. So all of these numbers fit this category. If I write instead x greater than or equal to, so I hit the greater than or equal to sign on the keyboard, which is just shift period for greater than, and then the equal to sign is right next to backspace. You can also use the math palette here. It's limited in its functionality. You're much more capable with the keyboard, but it does have a lot of the basics things. So like it has the parentheses, the greater than, less than symbols, X and Y. If you want to use that, you can just type X and Y though. You can actually type the letters here, which I don't know why you do that instead of using the keyboard if you have that available. And then the functions, this is very useful for a lot of cases. Of course, you can just type these in and it will understand what you're talking about there. And of course this thing, but you can just use the division, multiplication, which is the division is the a backspace next to the right shift. Multiplication is shift 8. That's the asterisk. Subtraction is just the same thing as a hyphen, which is to the right of 0, and then plus is shift equal, which is the number right next to the back, or the key right next to the backspace. I could have used this if I just hit backspace twice and then use this. You can see that I have greater than or equal to 14.3. I'm going to get rid of that since I don't really ever use that very much, only in special cases. But you can see here for this one, now we have a solid line. That's because we have greater than or equal to. So the point itself, it is a part of the solution. And everything above that, since x is greater than 14.3, all these points are included in the solution. So we have this part here and this part there, 2 distinct inequalities. We can create one that is together as 2 inequalities, since it does Desmos does understand tripartite inequalities. So that would be something like negative 1.8568 less than or equal to x, which is less than 7.49653. Okay, I'm going to turn off these first 2 just so it's a little bit easier to see. But as you can see here, it doesn't indeed understand this bounded value of x. X can be greater than this number here, greater than or equal to, I should say. It can equal that. That's why there's a solid line there. And then it's also can be less than this number. A strict less though. That's why you see again the dotted line, and it can be any value in there. I should also say that I've been just adding decimals. Let's do over 14, something like that. It understands fractions perfectly fine, and it'll give you the estimation. I think it always rounds to, let's see, typically it rounds to 3 places, but this one actually goes a bit further than that. But it'll round it on the graph itself. So again, I just want to make sure this is clear what I'm doing here on the keyboard. Something like do negative 14 over 3. I'm using shift less than symbol, which is just the comma on the keyboard, and then X. Let me turn that one off and zoom out a little bit. And then here I'm doing shift, again, shift comma, which is the less than symbol. And then I'm typing the equal button, and that automatically puts in the equal sign underneath of that inequality. If I hit backspace, you can see, let me add it in I'll do 78 over 5. Look at this line here. It's solid right now, but I can change that by hitting backspace, because technically this is 2 symbols. This is the less than symbol and then the equal symbol. I'm putting a comma between them. Oh, I can just do that. Yeah, I'm typing that to get the less than or equal to. If you just type it in one go, less than or equal to, it writes it that way. I created that space there between them to show it, but Desmos will automatically capture it. And so if I hit backspace on this, I'm technically deleting the equal sign. So you can see that if I do that, you can see now this line here is dotted. And if I'm still here, I hit the equal sign, now it's a solid line. So again, dotted, solid, backspace, equal, backspace, equal. That's just what all I'm doing there on the keyboard. All of this can still easily be done if you're unsure about it, just by using this. So when you normally will look at Desmos, we're not going to be using just this real number line here. Instead, we're going to see a 2-dimensional graph. That's because in these geometric representation of mathematics, we're trying to show a relationship between 2 quantities. And a single real number line doesn't really make much sense to show that relationship. So for instance, what I can do is I can just plot 2 points. So for instance, I say 4 and then 16. And you can see here that it's kind of hard to see what the relationship is between these two values, 4 and 16. You can kind of see that the way I have it written here, maybe this value is what I'm starting with, and then I have this value second. But if I flip these 2 values around, that doesn't really change how it's shown on the grid, on the line at all. And so maybe you can see that that this is the starting value and this is that. So which one is it? That's the pitfall of just using a single real number line. It helps to have a second one to know which one we're starting with through a convention, and then which one we end with. For instance, I could say that these 2 values are the square root, right? The square root of this number is this number. Or I could flip it around and say the square of this number is this number. And so you kind of have this failure of just the one real number line. Whereas if I had 2 of them, it's a little bit clearer because there's certain conventions we use. And normally you'd start off Desmos, when you go into Desmos.com, you're just going to see this is the starting graph. And that I just turned off the grid, which is very helpful for readability. This isn't necessary, but it's very, very useful. And then I turned off the y-axis. But now we're going to have both of them on there because this is more useful. And now what I can do is I can say clearly 416. This is the point here, and this is the point right there, 416. And the convention is always x first, which is the first number in the coordinate pair, 4, and then y second. So x goes to y. X is related to y. 4 is related to 16. And in this, at least in this case, my thought is 4 squared is 16. You could also think of, like a number multiplied by 4 is the second number, right? In that case, 312 would make sense. 3 times 4 is 12, but then 3 squared would be 3, 9. So it's just different how you're talking about the relationship. There's lots of different relationships out there, and sometimes we just state that they're related in some way. Of course, the nice thing about using this grid is that the x-axis and the y-axis are orthogonal, or they're meeting at that right angle. And that makes it clear, a clear distinction, because it's two separate directions, two separate dimensions, which is nice for the graphs and the visual representation of the relationship that we're talking about. Both x and the horizontal axis, which we always consider the x-axis for the standard convention, it doesn't have to be the x-axis. In a lot of cases, we'll use like the t-axis, but really it can be anything. But the standard convention, and the one that Desmos uses, is the horizontal. This axis is the x-axis, and this one here is the y-axis. And I'm saying axis because when you're talking about the real number lines, they're just real number lines. There's nothing special different about that, except the way we're representing it here. This is just a real number line that's going up and down, and this is a real number line going left and right. But in this context, in the Cartesian coordinate system, which is what we're working with, we call these axes, and that's what you're going to see here, x-axis and y-axis. So the representation that we're using here is using distances to designate points, and then we're going to use distances thus to designate relationships and all that kind of stuff. But it all comes down to the points themselves, right? 416 is always in reference to the 0, 0 point. 0 is a special number. In a lot of ways, it's very unique, and it's a great spot to use as the calibration point for the whole system, and that's why we call it the origin point. That's going to be point 0, 0, right there, where the two axes meet. Both x and y are 0. It's just a great point to use as the reference points. Now, every single point is in reference to this 0, 0 point, right? 416 is going to be 4 units to the right, since that's going to be positive 4 on the x-axis. We have 1, 2, 3, 4, and then from this point, we're going to go 16 units up. So there's 5, there's 10, there's 15, and the way these grid lines are marked out, that's going to be 16. So 4 is here, 1, 2, 3, 4, and then up to 16. There's 416. So it's really a measure of distance away from the 0 point. It's not a straight line distance. This is actually called a Manhattan distance, or the block distance, how you walk around a city in blocks. But that's the idea here, how we represent points and everything in the Cartesian coordinate system. Of course, I can show general points by using sliders. And let me go back to the home, which always takes us back to 0, 0 point, and then it fits it to your screen, whatever that might be. I can always use sliders, A, B, and that will give me 2 sliders. And now you can see that I have 2-dimensional movement here, because A and B give us both positive and negative. So I can, of course, now move the point wherever I want on this screen. It's not locked to just the x-axis. And of course, that gives me the ability to see these points, and I can zoom out as much as I want, and I can just drag the point around. And you can see it's changing the bounds that it was there, and now you can see these are the points. It's really only showing the whole numbers here. It's not using the decimal points. It'd be way too hard. There's an infinite number of points on this screen alone, and it can't, like, Desmos has to interpret it some way, so it's interpreting it as the whole numbers there, instead of also including the integers, or sorry, the decimal numbers. But if I zoom in a little bit and then bring this close to something I can actually see here, let me get it to 0, 0, so I can actually drag it. If I zoom in a little bit, then you can see that it's adding in those decimal points, because it can interpret it now. So you can see that the numbers here, right, if I go back to the home, they get positive as we go to the right and positive as we go up. negative as we go to the left and negative as we go down. And these axes, of course, cut this grid into 4 separate spaces. These are called the quadrants. This is quadrant 1, quadrant 2, quadrant 3, quadrant 4. We always go this counterclockwise direction in mathematics. So quadrant 1 is probably the most important quadrant in a lot of cases because it involves the positives of both x and y, which is very useful in a lot of real-world settings. For instance, if I think about x being the number of items that I sell, and if I have for each item I get a revenue of $7, then it would only make sense for me to talk about x being the values of 0 and positive, because I can't sell negative 3 items. That'd be like me owing items to someone. So I can show that by just looking at the 0 mark here, and then only the positive values. So let's do like 100 here. And then y in this case would be revenue. So it's not actually going to be y. It'd actually make more sense to label it as revenue. And you can see there, it's looking at revenue there. So I can label x instead of x by saying it as items sold. And you can see it's labeling it down here in this bottom corner. And then revenue. So if I were to talk about that, I can create a table of values. And in this case, x is going to be the number of items sold. And y in this case is going to be the revenue, which, oops, let me undo that. Control Z undoes, or you can just type this, or click this button here, or click this one to redo what you did. So it's nice to have all that stuff there. But in this case, we're going to have 7 times the number of items I've sold, which is x1 in this case. So I'm going to just type 7x_1. And now what I can do is I can just add in the values for x. So I can add in 0 for no items sold, 1 item sold, enter. Now it's going to say 2 items sold. 2 times 7 is 14. Of course, a revenue of 14. Then 3, 4, and so on. And what you see here is you see a plot of points here. 1 is there, and then 2 is there. So it goes up very steeply. And so what I'm going to do is I'm going to reset this axis here to be, let's start adding in, there we go. We can see it a little bit better now. Let's do 100. It's probably too much. And if I hit enter a bunch, you can see I'm adding points there. And it's kind of tedious to just keep hitting enter here. Instead, what I can do is I can add in a list. So I'm going to add in a new expression. I'm going to put it in front of this table here by just dragging it. Items. And I'm going to create a list here, and you do that with the brackets, the square brackets. That's curly braces, square brackets. And you're going to start off with the first number, and then comma, and then the next number, comma. You could add the third number. And Desmos will understand a list with ellipses, the dot, 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 as long as it's an arithmetic sequence. So it has to be a common difference between each one. So I could do 0, 1, 2, 3, 4, 5, 6, 7. That's just incrementing by 1 every single time. Or I could do something like 1, 3, 5, 7. It's incrementing by 2 each time. I could do maybe 15, then 28. That would be plus 13. So plus 13 again would be that'd be, let's see, 31, 41, then plus 13 again would be 54. I can show that here. But in this case, you can see that you don't have to type in the commas, but I like to do that just for distinction purposes. It's recognizing this as 101 elements. 1 through 100 is 100 elements, and then 0 is 101. And all I have to do is just put this list name in the first spot, and now it populates the entire thing. Of course, I have to change this now because I've changed the variable that it's talking about. But I just do that, and there we go. You can see now that we have this distinct linear growth. It's just a line that goes from left, from 0, 0 on upwards. But it's only in this first quadrant. Again, that it only makes sense in this first quadrant. I just want to show you that list that I had mentioned before. So if I did, what did I say? I said 15, then 28, then I did 41, and then I'm not sure where that would be going there, so I could do 15 plus 13 times 100. 1351 would also be in this. Sorry, 1315. And there we go. This is actually 101 elements, again, because of my multiplying by 100. And so I could use this, for instance, in this list. If I did that, let me just name this A here, and then use this as A, just for something different. There we go. And now you can see that this is a much longer because I did a lot higher values. But it's still this linear function. Again, and that's going to be the case because we're just doing 7 times that value. And once again, it's only in this first quadrant. All right, so that's quadrant 1. Now, quadrant 2 here, let me replace all of these things. I'm just going to delete these labels. Quadrant 2 here is with the negative x's and positive y's. And there are special cases where this is where you're going to be working in. But a lot of times you're going to see that if you're going to use quadrant 2, you're going to use quadrant 1 as well. For one instance, could be modeling a land distance here and then a height off of that land. So like this is the earth and then the height off of the top of the earth. So we can model that here. For instance, let's say that we have a river going from -10 to 10. Let me plot that here. -10 to 0, and then 10, 0. I'm going to use blue for that to designate the water bounds. So like this is a river here, and you can see that I have these 2 spots here to designate that. I could actually create a line there and make it all blue, but this is the simpler way of thinking about it. And then we can think about a bridge that crosses this river. Of course, it's only going to go in the positive direction, so it only makes sense to be in the first 2 quadrants. And one bridge that could span this river is something like this. It's going to be a little bit weird, but stay with me. And then we are only considering the bounds that are greater than 0 for the height. So we're going to create these bounds here from -25 less than or equal to x, which is less than or equal to 25. That just restricts this whole thing to the first 2 quadrants, this inequality here. Okay, so it's kind of hard to see what we're talking about, so let me change the bounds. Let's do from -30 to 30. And then I'm gonna go from 0. I'm gonna zoom out just slightly so it's a little bit easier to see, but 0 to 1. And this is a little bit dramatic of a way because obviously the bridge wouldn't look like this. It'd be much more shallow. But this gives us a lot clearer that we are indeed spanning this bridge. And again, this is only a height of 0.625. So it's not like it's super tall bridge that you're actually gonna have to drive up and over. You wouldn't be able to do that. But it shows it a little bit clearer what we're talking about. This is actually a parabola. This is a quadratic function, and it is spanning across these 2 points. So we have a bit of space here, not that much. If I kind of go back to the home screen, right? The space isn't actually that tall there, with the distance of the actual left and right distance when they're using the same bounds. But you have a little bit of space there, and then of course you have a little bit of gap between the water edge and the actual bridge there, where it meets the ground at -25 and +25. So that's just a simple model for the first 2 quadrants using a length along the x, and we're centered it at 0. You could of course shift this all over to the positive x values and only use quadrant 1, but it kind of makes more sense in this case because you have this symmetry here, -10 to 10. So it makes more sense to use both quadrant 1 and quadrant 2 in this context. Now, quadrant 3 is a little bit weirder because it is both the negative values, -x and -y. And typically, like if you have something that locates strictly in quadrant 3, it would make more sense to just multiply everything by a negative so that it becomes in quadrant 1. There could be some cases where this is where it's just better to think about it in this case. But a lot of the times that we use quadrant 3, we're actually going to use the rest of the grid because it fills in that one spot there. Alternatively, for quadrant 4, it's very similar to quadrant 1 and quadrant 2. Sometimes quadrant 1 and quadrant 4 are used because we like to think of the x-axis not as the x-axis, but as the t-axis for time. So for instance, if I label this as time, that's the y-axis. T-axis is time, and I'm going to label the y-axis as the height. For this context, what I'm going to do is I'm going to model a Ferris wheel. And to do that, what I'm going to do is I'm going to draw a table here. And I'm going to actually use, let me also put in a list here. If I'm going to go from, I'll go T, no. This will be from 0, 1, 2, up to 25. And I will put that in here. Okay, now I'm going to model a Ferris wheel by using this expression. Again, the expression is going to be a little bit weird, but bear with me. So this expression looks like this. Negative 25 cosine 2, and then I'm gonna type in pi here, and for pi you just type in pi, and it represents that. Desmos will automatically change that into the pi symbol. You can of course use this and just use the pi symbol right there, but pi will automatically be represented there. And then I'm going to divide this by 25 and put in x into there. I have to use, or sorry, not x, the variable here. Do copy and paste. Okay, it's kind of hard to see what we're looking at. And if I zoom out a little bit, I'm going to adjust the bounds slightly. Okay, and this is kind of what we have. We're referencing the height in terms, reference to the center of the Ferris wheel. So when you first get on the Ferris wheel, you're at the very bottom. And in this case, the Ferris wheel is 25 units, or probably like 25 feet in radius. And so you're 25 feet from the center of the Ferris wheel. And then, right, as time increments, it'll only increment in one step. And of course, it doesn't make sense to have negative time. That'd be going backwards in time, which we can't do. So we're only going forward in time, only in this positive direction. And for each time step, we're going to be incrementing. We're going to be going up on the Ferris wheel, around the circle. Let me actually draw the Ferris wheel itself, just so that we have a reference point that we're talking about. The Ferris wheel that I'm using can be modeled with this equation here. Just a circle. Y squared equals 25 squared. And I put this right here. It's kind of hard to see. We go back to so that the scale makes sense. It's not some weird scale there. So this is the Ferris wheel. We start at the very bottom here, and then we go up. And as we go up, we're going, for each time unit, we're going up like this. We go up faster as we go around here, and we go up slower as we're down here because there's more distance to travel. So it's kind of slow at first, and then it speeds up a lot, and then it comes to the top around here, top of this point. And then we're coming back down, but in reference to the center point, that's like we're just decreasing our height now. So we're just decreasing our height now. Time is still moving forward. That's the reason why we're always going this way along the axis. But then we reach the bottom again at this point here. So it takes 25 seconds to go around this circle, as long as there's no stops for any person. getting on or off the Ferris wheel. But like this is how you can model that. And of course, there's nothing special about stopping at 25. We can of course increase this to 100, and there we go. We have there's 1, 2, 3, 4 revolutions of the Ferris wheel, and of course you can keep going. You can get that to 1,000, and then you can just keep seeing. This is what models that behavior. And again, that was for the first and fourth quadrants, since we're dealing with time in this case. It makes the most sense to just work with those two. Sometimes it only makes sense to, we could of course shift this upward and model it from the reference of like the ground and your height off the ground. That would make sense. So like if I were just to do plus 25, I could just leave this all in the first quadrant. But again, sometimes it makes sense to look at the symmetry of what you're talking about here. And this is the symmetric kind of pattern that you see here with the circular motion. Desmos understands function notation perfectly fine. So for instance, let's look at this function here, f of x equal to x to the 5th power. For the power, I just used shift 6. That's the caret symbol that goes up into the power. So plus 6, and then type x, and then shift 6 puts it in the power. 4 plus 8x to the power of 3. Of course, you can, instead of doing the shift 6, you can just type, go into the symbol here, and then hit this button. This will put into a power. If you're using square, which is very common to use, you can just click this button here, which is what I'm going to do here. Square like that. Of course, if I wanted to, again, I'll just do 3x, and this puts it into the power. Generally, it's just the same thing as typing shift 6. And then, of course, you can put whatever power there you want. But the last one I want is minus 2x. So this is the function notation. You can see that it's graphing there. We can kind of ignore that for a second here. Function notation it's labeling this as a variable, and it's understanding the variable as this whole expression. And so I can create a table of values with that variable. There's no need to create a table of values since it graphs it automatically, but I just want to show you the value of it. So if I do -2, -1, 0, 1, and 2, and then here I'm going to just type in f of x sub 1. And it's recognizing when you plug -2 into this function and then doing the arithmetic there to simplify it down to a single number. And that first one gives us -20. If you plug in -2 in the x spots and then do the math, you get -20. That was -2, -20 is down here. And then the next one's -1 and -7 is right there. 0, 0, 1, 7, and then finally 2, 164. So that's going to be all the way up here. Of course, the way this looks, it looks like it's just a smooth line, but we saw that in the actual full graph, it wasn't. So you really would want a lot of points if you're going to do a table of values. Again, there's not really any need to, but I just wanted to just demonstrate this idea. So if I do like negative, let's see, 20, -19, 20. I name this as my x sub 2 values, and then I can just change this to x sub 2. Sub 2. You can get to the subscript by just hitting the down arrow. That gets into the subscript. The up arrow gets it back into the regular script. But now I have to change this to x2, so I just click on there. There we go, and you can see we have a bit more points. Kind of hard to see because of the scale. Let's zoom in a little bit to -20 to 20. Oops. And then, yeah, these values are super small and super large. So what we really want to do is you want to kind of put these values a lot closer since they're so large there. So let's go like negative 10 to 10. Oops, negative 10. Only considering, again, they're still really large. But what we can do is we can add a lot more points into there by just adding in the decimals. So negative 10, negative 9.9. Now you can see I've added a lot more points into there. And now we have this more interesting behavior. Of course, once again, this all isn't necessary because Desmos itself can just plot the whole function there. And that this plots a lot of points instantaneously, and gives a great view of what the actual graph looks like. If I go back to the home, you can kind of see that it has this waviness to it right there, kind of close to the origin point. Desmos understands function notation just as well, and of course this is the exact same thing as let me get rid of this table of values here. This is the exact same thing as just saying y, since the function notation is y equals f of x, f being the variable for it just stands for function, but it can be anything. It can be g, it can be a of x, b of x, all those things, or like function of x. Sorry, I need to do it here. Function. And so it recognizes all those things. If I turn off this, you can see the black is there. If I turn off this, you can see that the purple is there. It's all the same thing. But sometimes it's helpful to actually have a name for the function instead of just y. That's why function notation is so powerful in a lot of contexts.